I think it's recording. Yeah, now it's recording. If I don't see your questions, please go ahead and like unmute yourselves and ask the question directly, because sometimes I don't see the chat. Cool. Now let's start. So just to remind you guys, this GitHub repo has some bugs which you should fix yourselves. So you will run the code and sometimes you will get some errors, and you must identify where is the error and fix it quickly. And by you will also have to implement another function in the end after you run it. We will speak about it soon. Okay.
And what we need to do now, okay, with the, I download the iPad book of a lab, I download this repo.
Nice.
I unzip it, and what next?
Good. So what you will have to do, you just come here and try to run this train.py. Just try to run it. So let's just speak with about the files which you will find in this folder. So there's the config.py. Simply just it's a file which has configurations. So here you can find the device, either CUDA or CPU, replay memory capacity, update target, log interval, goal score, initial exploration, learning rate, batch size, gamma, and the environment's name. Now, your further task will be to change the environment and make the appropriate changes to both the model and the training algorithm such that it works with the other environment. Okay? Cool. So let's start.
One more time. What we need to change in the model?
Yes, you will explore that yourselves. So basically, you will run it. First, just run the code. It should run perfectly, no problem. And then we will change from this config, we will change the environment's name. Basically, what will change is the amount of actions we can make will change. And the code will have a what is it called? A bug. And you will have to change this bug to dynamically work with different sizes of actions. Okay, so it's mainly it's a very simple task. I just want you to find it yourselves. Okay, nice. So let's just start me personally running the code. Sorry. So here's what's happening. It's trying to learn, and here it's evolving. So we can see the number of episodes, the score, definitely the average score. It's improving, so we can see it's going up. And this is the epsilon, how the epsilon is decreasing. So, well, that's good. Manage participant. Welcome. So for the new attendee, please download the Colab link, which we sent, and try to run it on your own laptop using Jupyter. And try to also download or git clone this repo, which has multiple implementations of reinforcement learning algorithms in PyTorch.
Is there some implementation for Mario?
For Mario, the Mario game? Well,
yeah.
If OpenAI Gym has Mario Kart, well, let's see. If they have this environment, which I think there is one, small one, it's something you'll have to install on your own. And basically all you would need to do is take the image as an input, and you have, I think, limited amount of actions you can make. It's either go up, go down, go left, go right. I think not even go left or right, or is there? Yeah, so it's like
you can also
shoot. Well, it's,
yeah.
Again, so it's a limited number of actions, which means, as we did in the last lab, it's a discrete action space, meaning you can easily do it with deep Q learning.
But it's more time and power consumption to train, yeah?
Of course, of course. We will see that exactly on this exact game. So what we will do is we will train an algorithm which we will train a neural network which takes this. So which takes the environment. Yes, the environment state. So it takes the, so it does not take the image. It does not take the raw image of the environment. It actually takes the vector representation of the environment and trains a deep Q learning model to play the game. And if we explore the other options, which take actually the, what is it called? The image itself. So it takes this, it takes a screenshot of the environment and then makes the actions. This, of course, will take more time and take more compute power to play it well. So here we go. We can see that we were able to arrive to a score of 191. And here's the epsilon decreasing until it arrives to 0.1. So did you guys face any error or any bug while running this simple code? Please do run the code, huh? So you see actually how it's playing very well right now. It's like pushing back and forth. You can see it's how it's wiggling. It doesn't die very quickly. And this is in the 810th episode.
For me, it's not working.
What is not working? That's good. So what's not working? You will have to fix it, guys, okay? What's not working?
The algorithm starts to working, and I achieved the 14th episode, but when I just stopped for the reason.
Nice. Can you share your screen? Can you share your screen? Let me stop sharing. Share your screen, Ali.
And I just run it, installed the library.
Well, first of all, how can you fix the first warning? You see there is a warning. User warning nn.init Xavier is now deprecated in favor of Tata.
Is that I need to go and change something to something what is in euro?
So what you will have to do, you will go to this model.py line 21. Model.py line 21. You see there is initialization.
Just click by link.
Yes, just click by the link. Good. Yes, and change. No. Just change Xavier uniform to this Xavier uniform underscore.
Okay.
Just add an underscore in the end of the word. Nice. So now we got rid of the first warning. Let's read the error now.
Now it's error.
Expected device object of device CUDA, but good.
Maybe he ran on CPU. Maybe he have no NVIDIA card. I don't know.
No, I have the card and we installed CUDA.
Yes, so actually the problem is some of it is running on CPU, some of it is running on GPU. So go to the config and just make it all on CPU.
Just this one, yes?
Yeah. And run again.
Okay. Train. Go.
Do you see the model playing? So if you remember, in my notebook, in my laptop, we can see how the model is playing after he finishes training for 10 episodes. Can you guys now do this yourselves? So I want you guys to implement a function which shows you how the model is working every 10 what is it called? Every 10
episodes.
Yep, every 10 episodes.
I think we can just take the code from our notebook and it will be okay.
Well, yes, you can do something very easy. It's a very simple and easy function, and I need you guys to write it yourselves. So we can see that it arrived to a good place already. So it's 198, 190, 196. Okay, so it's safe to stop training now. So we see that deep Q learning was able to train the model and basically play the game better than better than a human would do. But this is a very simple game. Chat. What is epsilon? Good question. Let's go to the previous lab and answer this question quickly. So you were not here in the last lab, huh? Shame on you. So say that you're living in Innopolis and there is only one restaurant. So this Calcio Vino restaurant. You eat there a lot, and you like it. And then there is a new restaurant which opens, this Innomax new restaurant. And you, as a human being, you would like to eat something you want. So you would like to increase this reward function, which is the pleasure coming from food. Sometimes with a randomly, you would like to explore the new, the new restaurant. And with another probability, you would like to stay in the same place which you are familiar with. So basically this is epsilon. Epsilon is a parameter which, how do we say, controls this exploration versus exploitation mechanism. So basically, if you want to continue using what you already know, or you would like to ignore what you already know and just go with a random choice or a random policy. Do you get what is epsilon? Yes, thank you. So epsilon is just a method, just a number which helps you ignore what you have learned for exploration. So when we have 1, so right now we are not using our, what is it called? Our learned policy to make the decisions or to make the actions. We are following a completely random policy. So basically it's just random choice between the actions. And then it decreases. The more it decreases, the less likely it is that we will use a random action. If you go to the previous lab, you will see that how exactly we do that. So it's just a simple if statement. If we throw a random number, if this random is bigger than epsilon, so we follow this random, what is it called? If it's smaller than epsilon, so we use our random policy. If it's bigger than epsilon, we use our learned policy. Okay.
And if we have high enough score, can we set epsilon to 0?
Yes, you can. Like, can you? You can do anything you want. Nobody like you can ignore fully epsilon from scratch, like, because like your own policy in the beginning will be kind of random itself. So if you want to ignore epsilon at all, you can do it, but sadly it doesn't give good results. So if the question is, can you? Yes, you can do anything you want. Do you really want to do that? Not really, not really.
I mean, not in the beginning, at the end, then we have a good enough score.
Yes, but for example, your model is playing a very complex game, and at every time, please, can you explain again what is epsilon? So at every time, you will see a new environment kind of a new environment, which can surprise you a little bit. So if you continue using exactly what you learned without improving or without trying new things, you're not going to be good, that good. Let's say it that way. So take it in real life. In real life, if you are just doing the things which you already learn, or just using only what you know, you will make the decisions. You're not going to be a very successful person. But if you keep on exploring, learning, and combining both exploitation of what you know and exploring what you don't know, this will helpfully allow you to be better at what you do. So please, can you explain again what is epsilon? Epsilon is a number between 0 and 1, and it represents the probability of choosing a random action instead of using our learned policy. So the purpose about epsilon, nice. Hey, somebody shared a very good article about epsilon. So what is epsilon? So again, it's the probability. So reinforcement learning, our goal is to learn this something called as a policy. A policy just tells you what to do when you are at a certain state. So with a epsilon as a probability of ignoring what you know, with the policy that you know, and taking a fully random decision. So this is epsilon. Let's see. Yes, here it is. There we go. Explore. So basically, we will take a random choice. Exploit. We will use, basically ignore what's written here. So exploit means we will use our learned policy. Okay. And then if when we are doing the training, we take a random number. If this random number is bigger than epsilon, so we do exploit. If it's less than epsilon, we do explore. So this is the technique which allows us to do either exploit or explore. Exploit is using what you know. Explore is taking random options. Good. Now, can somebody share their screen and show me the algorithm running? With every 10 episodes, the algorithm will play for you, like just show you how it's playing. Remember, we did this last time. It was very simple. So basically, it's just a simple for loop or while loop with one extra command. So it's exactly this. It's exactly this code while not done. Just one extra line of code. Who remembers what is this line of code? The line of code which renders the environment.
In our notebook, it's not one line. Like it's a whole bunch of code to like.
Exactly. So environment.render. So you already have the code which plays in the environment. What you want is just to see how it's playing. So basically, all you need to do is just do environment.render. Environment.render will do the following. So it will, so you put it in the beginning of the for loop, and it will show you how the environment looks like. So basically, you will see how the model is playing the game. Хорошо? Okay, so I want you guys to go and build this play function yourselves and put it here. So this is the structure of the Thank you, Zoom. Thank you. Who thinks it's an easy task? It's very simple and easy task. Come on. Someone, please just share your screen and show us how to do this task. Come on. You will get bonus points. Nobody wants to do it. Sad. So here it is. It's a very simple function. Basically, it's while we are not done, you start with the, okay, somebody, brave person. Don't be shy, guys. I wish I could. Still setting up the environment. And the other guys, are you also still setting up the environment?
No, but where you find the play function? I don't know.
Good, you write the play function. I want you guys to write the play function. I've just installed Torch. Can you repeat what this function do? It's a very simple function. It's basically copy paste this for loop or this while loop, copy paste it, and add a small statement here called env dot render. That's it. That's the whole function. Nothing complicated. Ready? Come on. Come on. Somebody shares their screen, huh? Be brave. You did it. You finished already. Can you show us the function? Shame. So the function is pretty simple. Start with done equals to false. While we are not done, make one step. This is just for us, basically just for counting. We take get action. We use this get action method. Make the action on the environment. And the rest is the same. Just exactly the same kind of code we saw in the last lab. Let's look at this get action one. So get action, it takes a state, target network, epsilon, and an environment. If numpy.
Imad, could you please turn on your demonstration?
Oh, I'm not sharing my screen. Oh, sorry. Thank you. Yeah, sorry guys. So here we can see numpy if numpy.rand is smaller than epsilon, we will sample randomly from the action space. We will take a random action basically. Else we will use our own network to make the action. Who can tell me why there are like two networks?
Maybe like because of objects. Maybe we have like 2 points of failure.
Explore.
Maybe one net is controlling one kind of parameters, and second one second pair of parameters, and
they are exactly the same network. Let's look at it. Let's see. QNet, exactly the same network, same shape, same size, same everything. Let's look at them. Let's look at the network itself. Okay. So here's the network. Is this understandable? What do you guys think? So what is this? This
just
new
two fully connected layers and so
Hmm?
just two fully
Convert
connected.
from num of inputs to 128 and from 128 to outputs.
So it's a very small, it's a tiny neural network, which you can easily write, right? And then we just do this Xavier uniform initialization, and that's it. And then we go for the forward function, ReLU, Q value, done. So this is Q network. Q network tries to estimate our Q value, right? It's a neural network which takes a state and gives you Q values for the outputs, the different actions. Each action has a Q value at that state. Can someone tell me what's Q value for those who did not come last week? Q value. What's Q value?
Q value is the expected future rewards, total rewards.
Exactly. So it's what the model should expect to get as a reward in the future if he takes this action at this state. How does he learn this? With just a lot of iterations, a lot of work. He can build this big Q table. And if the, what is it called? The observation space or the state space is not something which is very easily put or representable in a discrete form, then we can go to something a bit more complex, which is a deep Q network. So for deep Q networks, you can see that there is no constriction on this inputs. The inputs are not constrained to be discrete values. They can be continuous values. They can be any type of values. If we want to put here a convolutional neural network and takes images, there is no constraints on that, right?
On images, maybe.
Maybe, yes. Whereas with Q table, for Q tables, they only work with
discrete actions.
Good. They only work with discrete actions and discrete observation space. Remember what's an observation space? The observation space.
Maybe set over like
It's all possible states.
states, yes, or all possible states.
Kind of. So the observation space is the representation of one possible state. So for example, we come to this game. The the representation of the possible state, if we remember, it has 4 values. The first one is the location of this black object, the angle of this, what is it called, pole, and the speed or the velocity with which they are moving. So we have 4 values which can easily or clearly represent the state. So this is the observation space. Cool?
Yes.
Nice. Now, just small question. Can you, like, the output of the neural network, and I'm not speaking here about Q networks, okay? The output of the neural network, if you can use a neural network, can it work with, what is it called? A continuous action space. So we said Q tables cannot work with continuous action spaces. Same thing for Q networks. But potentially, is there a limitation on neural networks which makes neural networks themselves unusable or non-usable in continuous action spaces?
No.
Exactly. So we can make a neural network which takes continuous input, continuous observation space, and maps it into a continuous action space, right? Potentially.
what our action is like non-energetal. Is like we have like infinite number of actions we can produce. Or what means
Yes,
infinite?
kind of infinite, but it's not really infinite. So imagine you are playing, for example, football. Okay, football. You are going to pass the ball, right?
Okay.
Passing the ball is not a discrete option. So it's not like when you pass the ball, that's it. You will pass the ball with a certain force at a certain angle. This angle is in 3D, so it's a lot of work, right?
Yes, you're right.
So this action, it's not represented in 1 or 0. It's not a binary action, more like a continuous action which has multiple values. So the angle of the action, the speed which you will make this action with. So it's many values, and they are all continuous. It's not just 1 or 0. It's not I pass the ball or I don't pass the ball. How do I pass the ball is also taken into consideration. Okay.
Okay.
Nice. So here we will come back to seeing something that we have seen last week, but a bit more neural network oriented. So what we will do, we will take the states, next states, actions, rewards, and there's masks. We make predictions. We make the next predictions. And I hope you can see there are 2 networks, and I will ask you to tell me why soon. Okay. Again, we said that these 2 networks are exactly copy paste of each other.
Due to time lag.
Hmm?
Due to time lag. It's just a time lag. Because we need a future prediction.
Kind of. We will see why. And again, another thing is we update this target network once every, let's see when, how many times do we update it? Sorry. Update target network. So we update in the beginning, and we update every update target. So it's a hyperparameter we could choose. Wait a second. Someone sent a message. Like don't use. Oh, it's okay. Sorry. So again, we only update them after a certain amount of steps or after a certain amount of epochs. Okay.
Okay.
Cool. After we make these predictions, simply we make the following. Remember this one. This formula.
Yes, you.
Who remembers this formula?
It's our reward, no?
Yes. It's +1. I cannot see your screen. You cannot see my screen right now?
No, it's old message.
Ah, okay. No, it's actually new. It's new. Artyom. Is this a problem only you facing, Artyom, or everyone else is also not able to see my screen?
I see your screen.
I see your screen.
Okay, so probably it's just
for the formula.
Okay, let me put the formula back again. Let's see. I see. Nice. Let's put the formula again. We used this formula in the case of Q tables. It was very simple formula, right? Same formula will be used to calculate the loss which we are using. Let's see. Yes. Think of it as just this simple formula. Okay? So basically what we want to do is we want to reduce the distance. So it's a regression. Think of this as a regression neural network. It only thing it has to do is to predict this value. So we give it this value, we can calculate it manually, and we ask the neural network to estimate this value. So it's a very simple regression neural network. The only thing is just the, what is it called? The label or the target which we want is a bit more complex, since it comes from like calculations of this formula. But these are all manual calculations, which we saw in the last lab, and they were quite simple, right?
And now I want to say what we have two networks which calculated first current state and current reward, and second model calculate their future reward, like a next step. Maybe the case?
We will speak about them soon. We will speak about them soon. We will speak why.
One more question.
Yes.
We're detaching target from the computational graph.
Yes.
And when do we update the target network?
The target network.
Yes, because it doesn't update it here.
True, true, true. So we see that there is one network which is not being updated. This one, the target network. And in this line of code, it gets updated.
Just the previous, next state.
Where?
Just getting the next state of the online network, yes?
Kind of.
And again, in this formula we have like gamma and some like next prediction. But what is the masks?
What are these masks? These masks, they come from batch. Let's go look at it. Memory, I think it's here. Yes, here are the masks. We send them while playing, or we make them. Mask equals 0 if done, else 1.
You want to say what is like our stop sign of the network? If we reached our goal, please don't do anything. Okay, thank you.
Okay, and you can see that there is this memory object which takes this name tuple. So basically, it's this is one transition. So the state, the next state, the action taken to jump from one state to the other, the reward which we got, and the mask tells you if this is the terminal state or not, or the final state. Yes.
Okay, thank you.
You're welcome. How do we make an action using our learned Q value estimator? So our learned policy. So we take the input, forward it through the network, we get the Q values, similarly to what we used to do with Q tables, which was a bit simpler than this. We take the maximum action inside this inside this Q value array and return it.
You want to say what we by this input, we say, okay, we in this situation on this state.
Yes. So the input is the state. And we calculate the Q value using our Q network.
And then we have like an array of like all possible actions, and we like score for all the actions.
Exactly.
And we choose the action with the highest score.
Yes, exactly that.
Thank you.
You're welcome. And that's what we do. So now let's go back a little bit and see this. So this code is a bit more complicated since it has some improvements. So first thing, we see that epsilon is changing. So after a certain amount of initial explorations, we will start decreasing epsilon. So in the beginning, we start with epsilon equals 1, meaning we will fully ignore whatever we are learning. We will continue learning, but we will not be using it. So basically, we will just make random actions and learn from these random actions for a set of iterations. So we come here. For 1,000 episodes, we will be running without any what is it called? without using our own model to guide us. Nice? We keep on.
Why so?
Why so? Yeah, exactly. This is just a improvement. So basically, the first 1,000 epochs, your model did not really learn something to guide you. So if you start trusting it right now, it's going to make a lot of bad decisions and can actually learn from it. And this is what we will speak about later during if we still have, hopefully we'll have enough time. We will speak about why learning from scratch, using it to learn from scratch is not a very good idea.
So it seems like your model is stupid for 100 epoch and you will ignore its decision, and after 100 or some number of epochs,
yes,
you will believe to it.
Yes, so basically we will ignore whatever the model says. We will go with a fully random decision and continue working with it. Another thing which you might notice in neural networks, before they are trained, they tend to give the same value. So whatever the input is, sometimes they just give you 0, 0, 0, 0, 0, 0, 0, 0. So if you train it just a little bit and continue following it, it will keep on giving you only one action. And if you continue making just the same action all the times, you're not really going to learn that well. So that's why it's beneficial to fully ignore whatever your model says and go with a random policy. Okay?
Okay.
And after this initial exploration time, so it's an exploration phase, we just keep on reducing epsilon every step and until it reaches 0.1. So at 0.1, we fix epsilon there and continue working. In some other cases, you will not see a linear decrease in epsilon. So you can find that epsilon decreases in some sort of nonlinear function. Either it goes with 1 minus exponent or something like that. What is the second network for? Nice. So remember, it's exactly kind of the same problem which we had of not being able to trust the network which we are using. So if you use the same network, so we take one network, use the same network to explore and to learn. You see that the model is repeating the same actions and not fully learning very well, because he makes an action and learns from it. That's bad. So what we want is make multiple actions, learn from them, accumulate a certain knowledge, and then use that knowledge to start making the actions again. So think of it this way. Mr. A has learned something. Nice. Mr. A will make a copy of himself called Mr. B. Let's use a screenboard. White screen. Whiteboard. Okay. So say there is Mr. A. Mr. A, he has learned something very useful, and he just makes a copy of himself called Mr. B. What's going to happen now is Mr. A will not learn again. So basically, he will not change his policy based on what's happening currently. Okay? Meaning, Mr. A keeps making decisions, whereas Mr. B learns from the new actions and environments, from the actions he's making. Nice. So now we have someone who is stable, Mr. A, he makes the decisions, and we have someone who is less stable, who is continuously learning, not making the decisions, but learning from them. After a certain amount of time, Mr. B has reached kind of, so it's not very influenced with the decisions that it made. So it's not very fluctuating, you can say so. So what's happening here is what happens after a certain amount of epochs from learning from new actions. We just make a copy of B. Something happened?
So we every time update network and B becomes A and A becomes B, and it's an iterative process, yeah?
Good. So basically it's as if using the same exact neural network, but with less fluctuations. So with less influence of what's happening right now on the decisions.
It's like, okay, I take the A, train it for 1,000 epochs.
Yes.
And when next 1,000 epochs, A makes decisions, B like learning on these decisions, but not making them.
Yes.
Then I just open and okay.
You see? So first, A makes decisions, does not learn from the decisions. He keeps on making the same decisions as if nothing's happening. B is learning from the decisions without making anything. So basically, if, say for example, right now, A made some decision which is bad or not bad, made a decision which led to bad results right now. With A continuing to making the decisions, overall, the performance increased. Whereas if you take the same network, which makes the decisions and learns at the same time, it makes a decision, reward goes bad, he will fully eradicate or remove this action which he made. So it will be more fluctuating in the decisions making, in the decision making process. You see? So what, by using exactly the same two replicas of the neural network, what we were able to do, we were able to make more stable decision-making process, hence more stable learning process. So why do we use both of these?
Because we want to stable and forward to success learning, maybe.
Good. So what we want is we want to make a stable learning process that is not very, very influenced by what's happening exactly right now. Okay?
It's like we like just like it's 1,000 is like batch size, or maybe like how many averaging of our like outcomes.
Exactly. We will speak about this right now. You will see a bit more information about it right now. So let's skip this. Skip the. Oh, let's not skip it. So let's go to the lab. Here's the lab. This is the notebook which we have. I don't think we have enough time right now. So I will go a bit faster, okay?
Okay.
We don't see it. We don't see it.
You don't see it?
Yeah, I suppose the previous page we see.
Now you see it.
Oh.
Nice.
Now, yes.
So this is exactly the same code, but the network does not take, what is it called? Does not take the environment variable, the environment representation, this. So it does not take the state as a representation, as a vector representing the state, but it takes the state as a picture like this, extracted screen. Here you will see the code for extracting the screen. Okay?
Okay.
And that's it. So it's mainly exactly the same code, but instead of learning from the environment, it will learn from the screen. Just to show you, it's, as you can see, just to show you that this technique will not really work that well. So let's run it. It will take a lot more time to build something which learns well. So what's happening in this exact second, the algorithm takes a screenshot of the environment and learns from it. And my laptop is being burnt right now. So it takes the screenshot of the environment and learns from this screenshot.
But eventually it will learn the same.
Eventually, yes. Eventually it will learn even better. Not better, I will not say better, but it will learn exactly the same thing, not that much different. But since the environment information provided, the information provided by the environment is more rich, this algorithm will learn faster and better. But of course, this also will learn, but after a lot more time. So learning from a condensed representation is always better than learning from the images themselves. And for that, what you can do to maybe increase the speed of learning, simply just take these images, encoder, decoder, learn some representation, latent representation of the environment, freeze your encoder, and train exactly this algorithm, which takes the state from the image, but you are doing less training using the loss of Q, using this Q loss. So basically, you're using autoencoder loss to train your network, and then just the final two layers are being trained using this Q estimation loss. Okay, let's just check the results so far, how they are. So here we are. We started very random, and then after a certain amount of iterations, it got to 35. 35 is kind of bad, because with random, you can actually arrive to 35. And it's keep on trying to learn. So far, it's bad, but with time, it will easily increase. So here's an increase there. But still. Okay.
I have a question.
Yes.
It seems like somehow similar to guns in some kind. Is there any papers about comparison between these two methods? I mean, I read for example, for photo generation and gun generation.
Good. We will speak how do they relate in something called as Actor-Critic. Actor-Critic models are exactly like GANs.
Oh, it's cool.
Okay, so we'll just go through another algorithm very quickly. It's called double Q learning. It's also implemented in here. You can find it. And there is something called as dual double Q learning. It is also already implemented in here. And you can run them quickly right now. You can fix some of the bugs they have and see comparisons of which one is better. You can guess that double Q learning is better than Q learning, and dual double Q learning is better than double Q learning. So let's just quickly go through the problem with Q learning, the algorithm which we just had. Say that there is your environment. This is your environment. You are at state A. You can go to state C, which is a terminal state with 0 reward, or you can go to state B, 0 also, and then from B, you can go to D. Now, the reward which you will get from D is, it's not a fixed reward. So basically, it's a reward which comes from a normal distribution of minus 0.5 and 1. Okay. So this environment is specifically made to show you the problem in Q learning. Of course, maybe it's not always like this. You will not be facing environments like this always, where the reward is quite random like this, but it's only here to show us the difference between the two. So what we will do is we have x1 and x2. Consider these as the rewards which we will get if we take x1 and if we take x2. Okay.
What means x1 and x2? Is like where we go? Or?
Yes, basically it's going to the right or going to the left.
Okay.
Just it's a small experiment. And the goal of this algorithm, the goal of, what is it called? The goal of, help me out. The goal of Q learning is to estimate this value, which is the expected accumulated reward. Nice. So let's try to keep track on it like this. So basically, we get a reward from taking x1, and we take its average. This is the average. Okay. The first reward was 3. The first average was 3. The first and second reward are -2 and 3. So the average is 0.5. And again, we keep on accumulating new rewards and updating this average. Okay.
But what's our goal? We want to reward will be like as less as possible.
No, don't worry about that. I just want you to understand the experiment first. Okay, so we get a reward, we save it, and we take the average of the accumulated rewards we are getting so far. So for example, if you go 3, then -2, then 4, the average of these rewards are 1.67. Okay. And then we take the action x2 and we do the same thing. So -8 was the first thing. So -8 was the first thing. So -8, the average is -8, -5, then it becomes -6.5, -8 again, it becomes -7, and so on and so forth. Now, the problem with Q-learning is it always takes the maximum over these expected or these averages. So the maximum of the use so far between -8 and 3 is what? 3.
It's 3.
Nice. The maximum between these two is 0.5. The maximum between these two is the following, and we continue doing this task. Now, if we take this, if we don't use Q-learning, basically we have no relationship with Q-learning, we will get that the average, what is it called? Expectation, the average Q or the average reward is exactly this one, -0.5, almost. You see?
Accurate or really accurate?
Yes, so it's almost -0.5. Of course, it's not perfect, but it's almost -0.5 because we are sampling from this distribution. So it's the mean of this distribution. But if we do as we do in Q-learning, and we take the mean over the maximums, we don't take the mean, we don't take the maximum over the means, but we keep on taking the maximum of the means, and sorry guys, we take maximum of the means, and if we take the average of that, you will see that the value is very, very far from -0.5. So basically what this is saying is that Q-learning always overestimates the rewards it will get. Did you understand that so far?
Sorry, no.
No. Let me try to repeat it very quickly. So what it's saying, if you what we want is to get the average or the expected reward, right? Which is basically the average of these rewards. Cool.
Okay.
How do we do that? We always ignore the other value and keep on using only the maximum. Okay, at each step, we take only the maximum.
Okay.
Q-learning.
Yes, Q-learning. Using this technique, if we go ahead and keep on doing this multiple times with averaging the results, we will get a very overestimation of the average reward we get. So in reality, the average reward, we know it, it's -0.5 because the rewards, they come from this distribution. Whereas Q-learning will tell you that the average reward is 0.09, which is completely wrong.
And one more time, what means x1 and x2?
These are the actions. These are the rewards you will get by taking an action.
It's just to experiment.
This is action 2. Okay.
Okay. Sorry.
Nice. So just quickly, so this is the problem. The problem is overestimation. And how do we solve it? We solve it by using double Q learning. I will share with you this link. It's very simple. It's very easy to understand, and it explains it pretty well. But we have to go to something a bit more interesting, which is actor-critic models. So actor-critic models are exactly what you said. They are very similar to GANs. So basically, you have a person which is doing the work, and you have a person which is evaluating his work. So similarly to what we said, where we have a fraud and a policeman, in this case, think of it as we have a child and a parent who is trying to teach the child to make better actions. So first we will start with what is actor-critics, then we go to A2C, which is very small change, and then we go to A3C, which is even smaller change. So they're very simple things. So we'll start with actor-critics. So actor-critics models are a combination of both value-based models and policy-based models. So we have value-based models which try to estimate or approximate the value function, and we have policy-based models which try to directly find the optimal policy. We don't have to. So instead of trying to find the value function and then taking the maximum value, we directly try to find the action from the state without estimating how good this action is. So directly finding what is the best action. Both of these are two approaches who are both good and bad. So what they decided, of course, they were like, let's make a combination of both value-based and policy-based models. So actor-critics is the following. We have an environment. The environment we have an environment, someone called the actor, he will make the actions on this environment. And someone called the critic, he will criticize, or he will tell the actor how to improve his actions. Good. So you can think of this as a generative adversarial network, or you can think of it as simply a mother and a child. So the child, the actor, is constantly trying new things, exploring the environment around him. For example, eats the toys, touches hot stuff, bang head against the wall, bad stuff. And the mother will criticize him, tell him, don't do this, or do this, this is good, you're doing such a good thing here. Don't do this again, do this. So stuff like that.
And how it's done in reality? By increasing or decreasing reward?
We'll see. We will see that. We will see that right now. So remember what's happening in, for example, GANs. We have a generator which generates a work or generates something, right? And then the what is it called? The discriminator will use that something to make a loss and train the generator. Cool.
Yes.
Good. Same thing in here. So we have the actor, he will make the action, and then we have the critic, he will criticize how good this action is. Can you tell me when was the last time where you saw someone or you saw a neural network able to give you the Q value of an action? Or the Q value is basically how good this action is or how bad this action is.
No, never in my life.
Nice. So we just saw that. So basically, what the critic will do is he will estimate how good this action is based on the reward function, and then he will send that feedback back to the actor, which will be doing the actions. Nice. So in simple terms, this is actor-critic models. So these are the kind of models which are currently dominating the field, especially with the new improvements. The improvement A2C, which is AAC, advantage actor-critic models. So instead of, as we said, the critic telling you what is the Q value or estimating what is the Q value. 1 second.
I have one question.
Uh-huh.
The critic is learning during training, yes?
Yes.
Ah, okay. It's not like Oracle.
Oracle? What is Oracle?
Oracle function. It's like a good predictor, predefined.
No.
Like who knows everything.
Yeah, no, he's also learning. Now, the advantage part of the actor-critic model, so this is the A to C, the improvement on it, it just, instead of estimating the Q values, what advantage actor-critic model does is he will estimate the advantage. Simply, the advantage is how better is this action compared to the other actions. So say at state A, you have, sorry, let's use whiteboard. Nice. At state A, I'm having some difficulties. Okay, so at state A, we have two options. First option has a Q value of 5. Second option has a Q value of 3. Advantage actor-critic model will not try to estimate this 5. He will try to estimate 5 minus 3. So he will try to estimate how much do I gain by taking this action over taking other actions. So this is the simpler, this is the other more advanced algorithm than AC, actor-critic. It's called A to C. Now, the latest version, or of course it's still improving, A3C, is called asynchronous advantage actor-critic. So simply put, it's having multiple versions of this A to C playing against multiple versions of the environment. I'm not sure if I'm sharing the screen. Can you see the screen?
Yes, now, yes.
Yes. So the asynchronous advantage actor-critic, it's simply put, it will take multiple A2Cs playing against different environments parallelly. So each one of these environments is different. So for example, this one has pink colors, this one has more greenish colors, this is dark mode, this one is the harder version, this one is a simpler version. So they are just different environments of the same game. We have multiple versions of A to C playing against each one. And then periodically what we will do, we will update this called a central model. It's also an A to C model. So we will update the central model, send our weights, keep on training these people, these workers will keep on training. And after they train, they will send their weights to this global network. Global network will update its weights, of course, not directly. It will not be a swapping the parameters, but just like accumulating. And then the global network will send the new version to the worker, and the worker will continue learning. So it's kind of very similar to what we had in small Q learning models. So here, with two versions of the same algorithm, but now it's a bit more complex. So we have not just two versions, but multiple versions, and they keep on accumulating their knowledge into the central unit. So this gives you faster training. It allows for the model to converge much faster. So this is, yes?
You want to say what decisions are made by a global network for all environments?
Yes, yes. Now, someone would say, why not just put the same environment and the same worker playing again and again? Same architecture, because they're all the same architecture. Now, putting different environments will put the model to learn different stages of the game, for example. So if you keep on using the same environment and the same model, that is useless, right? Because they will all be copy-paste of each other. There's no knowledge added by making it parallel. But if we put multiple versions of the same algorithm, learning from different environments, and then they share their parameters, this will give us a much more faster training. So this is the asynchronous part, because they are not swapped at the same time. So basically, it's not like worker A sends and worker 2, they are sending asynchronously from each other. So they're not dependent on when do we send our when do we update our parameters. Okay, so they don't update the same time. So they update depending on whenever someone finishes his work.
Okay, can I precipit to the original model actor model and say who is making decisions and who is learning? Yes.
Can you say that? That was a question, or?
Yes, it was a question. What in this model, who is like making the decisions and who is learning and when?
Both of them are learning. Who's making decisions is the actor. From his name, you can understand that he is making the decisions.
Okay.
And the critic will criticize the actions made by the actor, just in the same manner which GANs were working before. So here we have two neural networks which are operating against each other. Of course, reinforcement learning is a big field again, and new models are coming out every day. The sad part is, to train such models, it will take you like 400 days on humongous servers, basically on very big servers. So the sad part of that, we cannot really do a lot of work with it ourselves. As we've seen, a very simple Q network, which takes this image, instead of taking the latent representation or the environment representation provided directly, takes ages to train. Now, if we want to go for something more complex and more complex games, we will take even more time to train. So that's why I think most likely in the next few years, we will find something similar to what we have in ResNet, pre-trained models, which can play games very well. So do you have any questions? So about reinforcement learning in general? Maybe about your project?
Yeah. One problem is about the value-oriented, like how to say, value approaches and the policy approaches. And what's the difference? Maybe one more time. And who is better?
Oh, there's no such thing as better. There is a difference, but there's no such thing as better. So here we see that the value-based models, they try to estimate how good each action is at each state.
Okay.
Whereas the policy-based models, they will tell you at each state which action you should take directly. So they don't tell you how good it is, they will just tell you, take this action. You see the difference?
Yes.
Let me just do it privately after the class. Yeah, yes, we can discuss the product privately after the class. But just so that we can get a small comparison between these, each method has their own advantage. For example, policy-based are better for continuous and stochastic environments. They have faster convergence, while value-based are more sample efficient, so they train faster and steady. And you can check out his previous posts where he makes these comparisons. The secrets behind reinforcement. I'll send all of these references to you in the chat. So now I guess I should start answering your questions in privately. So who has questions about the project? Just send me a Telegram, what is it called? A Telegram message, and we will start
And who will grade the project? I mean,
Professor Fahim, I have zero information about how or who or what or anything. So basically,
you mean he also will check the code?
He will check the code. I have no idea if there is a code check or anything. So he will basically do everything about the project. So I have really zero idea. I cannot promise you something and then it's just
okay.
Yeah. So again,
when the demonstration will be?
When will?
Demo.
I have no idea, honestly. So these questions, don't forward them to me, forward them directly to Professor Fahim, because I can promise you something, but then Professor Fahim changes his mind or something, or so I cannot really make any decision in this regards. So please ask Professor Fahim the questions about the project, both the grading and when, and all of these techniques, the criteria for what is a good project, for how to grade the project, all of these questions. Professor Fahim will have more information about this.
Okay.
Mm-hmm.
Thank you very much for the lecture, for the lab. It was.
Thank you, guys. Thank you. If you have any questions, please forward them later through the Telegram channel. And if you want to ask me questions about the project, then try to make sure that they are questions which are not very helpful. So they're not like, how do I program this or how do I do this? Because I cannot help you. That will not be fair. And they are not questions
how
about
to make a project.
Yes, so don't ask questions like that, because that will not be a very fair thing to do. And don't ask me questions about the grading, because I cannot lie to you and tell you I know something about the grading.
Okay, thank you.
You're welcome.
Bye.
Bye-bye, guys. Have a good day. Stay safe. Okay.